Hello everyone, this is Anthony Chen. I am very excited to present our work at CVPR 2023. Our title is PiMAE, Point Cloud and Image Interactive Mask Autoencoders for 3D Object Detection. In real-world scenes like autonomous driving and robotics, these agents usually collect image and point cloud data using the RGBD sensors for visual perception. Yet, it's quite expensive to annotate enough 3D data to train a good agent. So to ease the problem, we propose a novel multimodal self-supervised pre-training scheme on unlabeled point cloud and image data. We first extend MAE from image pre-training to point cloud and image multimodal pre-training with 3 novel cross-model interaction designs, which we will elaborate later. And our pre-trained models boast performance of 2D and 3D detectors by a large margin. Now, I will introduce our work in details. First, as I mentioned just now, we can collect low raw point cloud and image data using the RGBD sensors. And these two modality data are naturally paired together, free of annotation. And now we will need a suitable self-supervised method to train our model. Contrastive methods are quite popular these days, like CLIP, but it depends heavily on data augmentation, which might harm the correspondence of the paired data. And mask autoencoders, simplified as MAE, was proposed in 2021 and has gained large popularity in computer vision for its simplicity and efficiency on image pre-training. The core idea of MAE is to apply mask to an image and train an encoder-decoder network to reconstruct the original pixels. Although there exists MAE on image, on point cloud pre-training, respectively, but unfortunately, there were no MAE performed on point cloud and image multimodal pre-training yet. And yet, the current multimodal MAE methods are kind of lack of modality interactions. For example, in multi-MAE and M3AE, they all mask out different modalities in a random manner and do not consider the correspondence of them. Here's a methods overview of our work. First step, we need to embed and mask the two modality input. Given a paired point cloud and image data, the point cloud will be tokenized through furthest point sampling and k-nearest neighbors algorithms, and randomly sampled into some visible point patches. Next, the image will be sampled through our novelly proposed complement masking module, where we project the points onto the image, and if the projected point patches is visible, then the corresponding image patch will be masked. And this way, the masking pattern between the two modalities will be complement and thus reduce cross-modal information redundancy, encouraging the network to look into information from other modality to complete the reconstruction of their own modality. Next, the sampled point patches and image patches will be embedded through a mini ImageNet and a linear layer, respectively, with added precisional embedding and modality embedding. Then the embeddings from two modalities will first go through a modality-specific encoders and then concatenate before going through a shared encoder. Then, we add some learnable mask tokens to the encoded features with added precision embedding and modality embedding. The full set of features and tokens are sent to a shared decoder and then separated into modality-specific decoders to get decoded features. Finally, we construct the input and point cloud image using the decoded features with a linear layer reconstruction head. We apply transfer distance loss on the reconstructed point geometry and input geometry, and apply MSE loss on the reconstructed image pixels and input image pixels. And then, in order to promote the knowledge transfer from two modalities, we propose a cross-modal reconstruction module where we ask the 3D features to reconstruct corresponding 2D features and apply an MSE loss on them. Here's our experimental setup. We first pre-train PiMAE on some RGBD dataset for 400 epochs and apply no data augmentations. And to evaluate our method, we perform experiments on Sun RGBD, Scanner V2, KT, CVPR, MiniGMNet, and FC100, and uses DTR, 3DTR, Mono DTR, Group VCD as our baselines. Here's our results on 3D object detection. We improve 3D TR and Group V3D by a large margin, maximally 2.9% on Sun RGBD with the AP50 metric. And also, we provide results on 2D object detection on Scanner V2 and monocular 3D object detection on KT, which is actually a out-of-distribution data comparing with our pre-training indoor 3D data, and we still improves the baseline's performance by a quite large margin of 3.5%. Our model also performs well on few-shot image classification setting, and where we surpass previous point cloud and image self-supervised method cross-point. And we also done a series of ablation studies to examine our proposed designs and found it non-trivial to interactively learn point image features. For example, we tested our masking strategy, our reconstruction target, and the modality influence. And also, we try to fine-tune 3D TR with limited annotated data, and we outperform baseline by a large margin, showing PiMAE's generalization ability on data efficiency. And here's also some ablation studies on model architecture and masking ratio. You can check out for the details descriptions in our paper. And also we provide some visualizations in the paper, including the reconstruction results, where PiMAE reconstructs image and point data simultaneously, and also some cross-modal attention features extracted from the last layer of our modality shared encoder, showing a strong cross-modal understanding. Also some 3D object detection results. So to conclude, we are the first to explore pre-training MAE with point cloud and RGBD modalities interactively with 3 novel schemes, including a complementary cross-modal masking strategy, a model shared decoder, and a cross-modal reconstruction task. And through our extensive experiments and ablation studies performed on data sets on both modalities, we discovered that PiMAE has great potential improving multiple baselines and tasks. Thanks for watching.